Start recording. Here we go. So, what are we talking today is about inheritance. So far what we have seen is a little bit of build systems. I hope you understood what happens when you link two pieces of program, when you compile a CPP file into a binary. And we made a little bit of operator overloading. We started introducing the classes in C++, copy constructors, and destructors, and whatsoever. This is like basically what we have done so far. Today we will add another bit of object-oriented programming to the C++, and we will talk about inheritance. And we will make a very long exercise that I will code with your suggestion. And the goal is that at the end of the lesson to construct some sort of virtual simulator that will implement all the concepts that we have seen so far. I will be more clear, like at the end, and at the end when I will explain what this simulator is. But so far, let's talk about inheritance. I mean, first question, how many of you have heard about inheritance so far? How many of you didn't? Excellent. Also, inheritance is a concept that, for those that didn't do it, is like basically an object, a class inherits from another class, means that a new class that inherits from the previous one has all the members and all the fields of the original class plus its own. Okay, so an object of an inherited class is also an object of the base class, which is the class from which we inherit. And inheritance is heavily used in many contexts. For instance, the most classical are the Windows systems. In the Windows systems, when you want to create your window in your environment or whatsoever, it's not that you start implementing from scratch a window class or whatever that does the impossible, that interacts with the video driver to do the rendering of the window itself. What you typically do is that you take a base window, you inherit from an existing class that has all the nice properties, and then you override some behavior in the inherited class from the base one. But we will see examples in a while. So that's one difference. Probably all of you, like, despite those that didn't know inheritance, the others experienced inheritance in Java or in Python. Now, I don't know Python, but in Java, the inheritance can be only achieved by deriving from a single class, which means you have a base class, and then you can have multiple classes that derive from this base one, but every class has only one parent, has only one originator. Okay? I don't know in Python, does it support multiple inheritance? It should, but I don't know.
I think yes.
Okay. But in C++, a class can derive from multiple classes. Okay? Which means, for instance, I have a class which is the printable object. I have a class which is the drawable object, and I could have a new class, for instance, point, and that could implement the drawable function and as well the printable functions. It's very much similar to an interface in Java. Okay? So you can have multiple classes. Now, a derived class or a struct, because there's technically no difference in the compiled code between a class and a struct, it's only a convention, has all members of the base plus its own things. Another important thing, a pointer or an object of the derived class, also an instance, is also a pointer to the base class, but the opposite is not true. So if I have a class person and a class student that inherits from person, a student is also a person, but a person is not necessarily a student. Okay? Which means that assignment complies with this rule. So I can take a student and assign it to a person. If I do so, I will copy, if it's a concrete object, so not a pointer, I will copy into the student struct all members of this into the person struct all members of the student struct that are contained that are contained in the person subobject that it contains itself. So I copy only a part of it. Also, another thing, when deriving a class, the constructor chain should be preserved. What does it mean? When we were writing constructors, we have seen that we might decide to override the default constructor. So there is the constructor of an object, the one without arguments, which is given for free to you by the compiler, which typically does nothing. It doesn't initialize fields, it doesn't do anything. If you want to override it, or if you want to prevent the people to create an instance of that object without passing some parameters, that's what we do when we define a constructor with arguments, okay? What happens is that if you have a derived class from that base, you need to initialize, you need to initialize the base class by passing some argument as well. So you will have in the derived class to call the constructor of the base class. A little bit similar to what you do in Java when you call super, okay? You will have to do something similar in C++, but for all the parents that this object might have, okay? Now, let's see examples. Like this is the generic definition of like how you define inheritance. You have either a class or a struct, then you have the name of the class that you are defining, and then you put this thing colon, these 2 points, and then you write either public, protected, or private, which is 3 qualifiers. For now, just to think everything is public. And then you write down the base type. So if this is a class A1, a class A2, I could define a class B that inherits both from A1 and A2 in this way here. That clear? And every time you put a base class, so in this case B derives both, is a children of both A1 and A2. Okay, very similar to Java. I don't know what about Python, but that's it. For each class, you have to specify whether for each base you have to specify whether it's public, private, or protected. Now, let's see an example, and obviously I will now go to the editor. Like when you have the code in the slides, there's always a pointer, you see, so on some source that is in the folders. So I will open it in the editor because it's much more meaningful. No, 0, 2. Okay, let me do this. Big enough? Bigger? Ah, good. Okay. So here we have a stupid struct A. Silly. Struct A that does nothing else than having a constructor with a value, with a number, like having a data member, and this member is an integer. The name of this member is my value. Then we have a funny constructor which takes an argument and initializes the member argument. Then we have a destructor, which does nothing else. Like if you wonder what I'm writing here, I'm writing simply A, and then a point. This is a keyword that inside a class means, inside an instance of an object, means a pointer to myself. The same as this in Java. Okay? Then it says I'm a constructor, so that we can see for that specific object, for that specific pointer, when its constructor is called. And also we can see when the destructor is called. Same story, the tor. And then we have an incredibly cool method, print, that what we'll do, we'll print the class, writing print, like this string, then it prints the pointer to the object, and then it prints the value contained in the class. So far, so good. Very stupid object, okay? We will do something funnier later. Then we have a fantastic class B, which is deriving from A, which means that an object of B is also an object of A. Okay? So in B, I will have all data members and all functions of A, only that I don't need to copy them over. Clear? Then I have a constructor without arguments for B, which means that I will be able to create B without anything. But here I have a problem, because in the class A, I have derived a constructor with one argument, and this automatically destroyed, eliminated, has hidden the default constructor, the one without arguments at all. So when I create an object of B, I have to initialize an object, the object of A, which is contained inside. But the object of A doesn't have a default constructor. And since it does not have a default constructor, I need to call explicitly the constructor. And how do I do? Well, in C++ you have the so-called initializer list, which means after, in the constructor function, after the definition, after the parenthesis, this is like the constructor, the signature, you have column, two dots, one on top of the other, and then on the bottom you write basically all the variables that you want to initialize. In particular, you want to call explicitly the constructor of the class A contained in B by passing as argument 0, which means that you will be calling this thing here with V equals to 0. And also, you notice another use of the initializer list. You can put a comma and initialize all the base classes that you might have, but you might also initialize data members in the initializer list. So here I'm saying my other value, what is my other value? It's an int, defaults to -1. That clear? It's just to show you the initializer list. You can, this is completely equivalent to do this. Right? If I would do this, I could delete this statement. Only that I know that the initializer list is there. I'm using it just also to show you the initializer list. It's important that you realize that the the destructor chain is preserved. Then I will later on delete this line from the program, and you will see that I will get a compilation error, because the compiler tells me, hey, you define the constructor of B, but how do you construct the object of A, which is inside B? Which parameters do you give, given that you have overridden the default constructor by doing this action over here? That clear? I could solve the problem also by doing this. A in this case, I would have defined the default constructor, and then the situation would be preserved. But I don't do it. Maybe because this object doesn't allow to be initialized by design, without parameters, okay? And then we have a fantastic main that later on I will delete this thing, and I will show you what happens. I have a main. What is this main doing? Prints an handle. I don't know why, because I like it, probably because that's an handle. Then it prints a create A. Then it defines an instance of an object a capital A object A, with a value 3, and it prints it. So here I always expect to see an invocation of the constructor, and then the method print. Correct? Then I create an object B, and I print it. So far, so good. And then I have an extreme fun in creating an object of type A1 that I initialize through the default copy constructor, which means copy all the fields, to the object B. But B is an object B and A is an object A. What happens in this case? Well, all members of the class B that are also in A are copied into the new instance. So in B, so B will contain an instance of my value, which is referred to the class A, which means that A1.myValue will be equal to B.myValue. That clear? Yes? You're copying the struct inside. This object is many objects, and then whenever you do an assignment, you do a deep copy of the memory of this part, but only for the part that is common. Okay? Clear? Okay, let's compile this spectacular piece of program. I'm just compiling command line g++ minus O04 inheritance 04 inheritance. Okay, I expect to find here a piece of thing. Yes, you see that it's a binary which is called 04 inheritance. I start it 04 inheritance, and I see exactly what I expect to see. The first I see the constructor of A, object declared on the stack 07ff, and then I see the method prints, which is called on the very same instance that I created. Then I have fun in creating B, and here you see the constructor chain called by B. The constructor, when you construct an object, you've implicitly all constructors of the base classes are invoked. And so here you see that first is called the constructor of the instance of the object A inside B, because B derives from A, and then is called the constructor of the B class. This is automatic. And it follows the initializer list. Then we have this sequence of print, A print blah, 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 so A as value 0, B print as prints the other value, like only the other member, -1, and then I think I have the assignment operation. Where was it? Yes. Here I create the other object, A1, so I expect to see another constructor. No. Is it correct? So a B print, a Ctor, this is, I don't see a constructor. Because there's a copy constructor, right? Yes. Haha. Why? Yeah, this is a nice question. Here, in this list, I would expect to see that a constructor here is invoked. Do you agree with me, guys? But I don't see it. Why? I would expect to see some printout. Because in this action over here, this action, what is this action doing? It's calling the copy constructor. Okay? But in the class A, I did not override the copy constructor so that it prints, hey, I am the copy constructor, you're printing me. So let's fix this. Let's add the copy constructor. Const A %. My value. I'm adding the copy constructor. And then, of course, I want to print it. Copyctor. No?
Yeah, it's between my other value and equal -1. It's there. It was there.
Sorry?
It's there.
It's there? Yeah. I didn't see. Copyctor. Yeah, sorry. Yeah, I didn't see it. I have to print it bigger. Okay. Copyctor. Now I have overridden. I instrumented my code in order to print what's really going on. So I expect to see this copyctor, and then I invoke the method A to the new method, to the new object A that I've created that prints my value, which is initialized to my value of B. Okay? Because I operated the copy. And here I have the funky destructor chain. This is interesting. When I destroy an object, also the destructors are called in an order which is the reverse of the order of the constructors. So first I call I invoke when an object is destroyed. First I invoke the destructor of the most derived class, and then of the parent class of this, and then so on and so forth. So the very first object that, and also another interesting thing is that you see that the objects are destroyed in the inverse order of creation, because they are pushed on the stack, and then they are popped from the stack one after the other. So this is the first object which is created, and this is the last object which is destroyed. This is the second object which is created, is the same. And this is the first, it calls the destructor of B, and then implicitly it calls the destructor of A inside B. Okay? And then the last one is the last object that we created. This is just to show you, this is a very simple inheritance with objects on the stack, which means that we are copying the data physically and deeply from A to B. Okay? All right. Questions on this side? Sounds a little bit magic. It's not. It's like a binary copy of a substract. That's what happens. And the destructor chain and the constructor chain have to be preserved. Oh, yes, there is one thing. I promised you that I show you what happens if I delete this line. If I delete this line, and I try to compile, this is a compiler that complains. It says, hey man, in this constructor here, you are trying to initialize, this is the B class derives from A, but A admits only one constructor, which is this one over here. In the class A, you don't have a default constructor, so I don't know what to call here. That's what it says. And then it presents me candidates which are no, I don't want to see. How do I recover the thing? Well, I explicitly call the constructor in the initializer list. Clear? Let's go back. Okay. Then this was the test main. Oh, shall we try also the opposite? Shall we try to assign to an object of class B, to an instance of an object of class B, an object of class A, and see what happens? You know, now we took a base and a derived, and we assigned it to base. Let's see the opposite.
Since I'm coming from Java, when we assign from particular to general, we can, because there are members.
But here you are assigning from derived to base.
So the
let's try the opposite, I said. I'm not saying that it works.
Okay.
I'm saying let's try the opposite, let's see what happens. And then let's reason on what. Exactly. But B2 equals A, 1. Will it work? It can't work. It can't work because B is bigger, B is bigger than A. B has an instance of A, but has its own fields. And so if you try to assign something, it says, hey, but what do I do with these other fields? But let's see if the compiler agrees. No? Complain. And technically, the compiler told me, hey man, I do not know the operator equals between an object of class B and an object of class A, because you could also define an operator equal, and then in this case, this would work. It doesn't say it's wrong. It says, hey, maybe you forgot to implement it. But in this case, it's wrong. Of course, if you implement an operator equals that initializes by 0 all the fields of the object B, that this could work. Or that copies, nitpicks only the things of A that are interesting for you. All right. Back to the slides. Oh, let me see if I'm recording. Yes, I'm recording. All right. Now, that's a lot. That's another thing that we have to say. But before that, the rule of C++ is that you pay only what you use. The inheritance implemented in this way is very trivial, it's very simple, and it's also very simple to translate it in machine code. Because all what you do is basically, you could do the same with C, with structs. You don't have magic things behind, right? But that's one thing that is very powerful in Java and in general in the object-oriented programming, that it's the late binding. In Java, you only have late binding, which basically means the overriding of a method. Okay? So when you have an object, like what happens is that, like to explain to the C experts, what happens is that you might have a class which has a behavior, let's say print, okay? And this is the base class. But then you derive this class and you would like to redefine the behavior of this function in a class of the derived object. So that print may be, in case the print of a student, a person will print the name and the family name, the print of the students will print the name, the family name, and maybe the student ID. Okay? But still, you want to have one single instance of method print, so that if you call an opaque object that could be a person and you say print, then it prints the right thing, depending on the instance of an object. Okay? So, in Java, all the methods support overriding. So it's something that you are so familiar in Java that you don't even consider. But in C, no. In C, or in C++, you can define that only some of the methods support overriding. Because overriding incurs in a performance penalty. Overriding, technically, when implemented, requires the computer to jump to a table and to figure out, depending on which class you have, which method to call. So you have an indirect call, okay? And you cannot inline the code. You cannot do some brutal, aggressive optimization that otherwise you could do. So in C++, if you need overriding, you have to choose which methods in your base class will support overriding. Is that clear? The methods that do not support overriding are attached to the class and they are called at static time. Means they are resolved based on the type of the variable that is declared in that moment at compile time. Like for instance, in this case, if you would call, let's assume that these are two pointers. In this case, if you would call the method print of the object A1, only the method of the object A would be called, not the method of the object B. In this case, it's correct because we did a concrete assignment. With pointers, it's a little bit different. I have been unclear, I'm aware. Let's do an example. Like the important thing is that if you want to declare a method that is subject to overriding, you have to use the keyword virtual at the beginning of the function into the declaration. So virtual, blah, 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 and that's it. And then whenever you are overriding this method in the derived classes, you have to use the override clause after the signature of the function. So before the curly bracket that defines after the closed argument list, after the closed parenthesis, you write override. Okay? And then you can still access to the methods of the base classes. Let's see an example. And let's see more concretely what I meant with late binding thingy. 07 late bind. You have these files into the old folder, then I will reorganize it to match the title of the lessons. 07. Okay. Now, this is the simple thing that we have. We have our usual class A that implements a print method. We have our usual class B that derives from A, and we have two methods, the method print of A that prints A, and a method print of B that prints B. Does it shock you? It's the same thing that we have seen before. Okay? Only that I did not instrument the constructors. And then we have a fantastic main. Only look at this part of the main. And this is the interesting bit. We have an object of class B. Fine. We initialize the object of class B with 10. Then we have a reference, right? A reference is not a concrete variable. Remember what a reference is. A reference is a dereferenced pointer. So the address of A ref will be the same of the address of B. The memory will be the same. What does it mean that? That the objects are the same instance. A ref and B refer to the same instance, so the same concrete object. That clear? Very good. Then if I call bprint, which method do you expect to be called?
The one plus A.
The one of B. No, B print. B print, here. B is here. B is still living. No, it's another thing. Compiler doesn't know that they are the same. So print. Then it will print this business over here. That clear? And if you call aref.print, what do you expect the system to call? bprint. How many vote for bprint? How many vote for aprint? Okay. Now, I said that to call the right, what is aref at compile time? What is aref? Is a ref at compile time? What is the type of aref? Reference to A, right? Reference to A. Compile time, right? If it is at compile time, the compiler can resolve this at compile time, so it can call the method print without having to reason about the identity of the object. Because it doesn't depend on the instance. It doesn't depend on the value of the reference. It depends on the fact that that object is a reference, and the type of that reference is a ref. That clear? So in this case, it will call the method print of A, because the compiler is stupid, and it says, hey, this object here is a reference to A, right? Did I, no, don't look at this. This is a non-late binding example. No, yeah, this was the classes that we have seen, right? There's no virtual in here, okay? You ignore this, because it's all in the same source. Where was it? Here. What I expect, why? Because I didn't put any information. In order to implement this machinery of late binding, I need to add to the physical layout of an object, to the memory, some additional information. Like, for instance, the identity of the object, for instance, which method to call when, and so on. These objects are stored in a thing which is similar to the class object of Java that in C++ is called the virtual method table. There is one instance of a virtual method table which is linked to all instances of object belonging to that class. It's just a map of pointer functions. Anyway, so said, do you understand why this happens? Of course, if I would have done the thing that I expect to do, see, if I would have defined this method here, virtual, in the base class, and I would have said that it overrides in the derived class, even if override is not required, because it's implicit, I like to put it whenever I override a method so that the compiler checks that it's really doing an override for that method. Because sometimes you make a mistake, you write print, and then you say, why doesn't it work? Okay? Now, and I define two classes. The only difference is that here you have a virtual, and here you have an override. The methods, they have the same signature. Then if I do the very same thing, which is, you declare a LB. Let's see. Same example of before. I declare this object, I declare a reference to that object that initialized to the object, and I call the two method prints. In this case, thanks to the virtual clause, I'm calling, I resolved the right function to call at execution time. Which means that only at execution time I can know what the class, what the variable aref contains. Imagine that this aref could also be living in a function, and so it could depend from a parameter or something. At execution time, I look into the object, the object pointed by aref, which was true instances B, okay? And I call the right method print. But then, let's do another thing. We create, and this is more bad, here I'm creating a copy of B as A. So I'm creating an object that I call ALB, okay? So it's, of which class is it? LB stands for late binding, okay? So these two were the two classes copy of the other ones, this one and this one, ALB and BLB that just implemented the late binding. Okay? The difference between two is only the virtual and the override. Agreed? What do I do here? observe, observe, I create an object on the stack of type ALB. And then I initialize it with a copy constructor, which means that I copy inside this variable over here, physically, all the members of B that belong to A. Okay? So now, what is the true type of this object? A. So what this method here will be calling? A print. Because here I'm doing a deep copy. If I'm doing a deep copy, I'm creating a new instance of an object. And the instance of that object is the instance of a variable that I declared. Okay? Very good. I imagine that you want to see compiling, right? 07, 07 late binding, 07 late binding. Okay, exactly what we expect to see. In both cases, so for the what the print method calls, so let's put it aside. Let's see, I can do it also from Emacs. Control X0, Control X3, make it wider, Alt X, shell, boom, 07, okay. Power of Emacs. So our main was here. This is the part, observe how I use the scopes. Here I wanted to declare to write the very same program, and so I created two scopes, because only the variable that live here, they will be destroyed after I leave this scope. Okay? So I create an object of class B, I print it, and I invoke the method print of A. Then I call the method print on the reference to that object, and it calls A, because this version was without late binding. But then I do the very same on the bottom. Very first print is correct, is BLB, but also this print is correct. Okay? Because of the virtual machinery. And finally, as you all spotted, ALB is called because the true value, the true type of ALB is of copy of B as A is ALB. Clear? See? Okay. Very good. Late binding, example, dynamic cast. Okay, now it's useless to say that the same rule of assignments that hold for reference and for types hold also for pointers to objects. So it is possible to assign a pointer to an object of class B to a pointer to an address of an object of class B to an address to a pointer whose type is address of object of class A. Okay? Same as you can do with references, you can do with pointer. And it's also not possible the opposite. Same rule as in Java, so you cannot assign a base class to a pointer to a base class to a more specialized class, because otherwise you would be violating something. You know, this object here would have more stuff. So, and there's also another thing that you have in C++, which is the runtime type identification. What is it? It's a mechanism that allows you to know at runtime what is the type of a pointer. Okay? But this works only if that variable for which you are declaring the pointer contains inside a virtual method, a method of which you have done overriding. Because only in the moment where you decide that an object is a class is subject to overriding, then only in that case the compiler will generate the code and the runtime system that contains the class object of that method. Otherwise, a class is exactly equivalent, also in terms of memory footprint, to a struct of C. That clear? Only when something is virtual, the system takes the effort of creating a virtual method table for that object. Because if there is no virtual method, then everything can be static. It's going to be faster, it's better. If you don't put a virtual method, you will not be able to do the dynamic cast. So let's say how it works. Well, dynamic cast has this weird signature that we will understand in the future. Let's look at this simplistic example. We have an object of type BLB. We like it? Yes. An object of type ALB, once again, and then we declare two funny pointers. Both pointers are of type ALB. Okay? A pointer that I call A pointer that takes the reference to A, and a pointer that I call B pointer that takes a reference to B, but ALB, this object here, is of type pointer to A. Okay? And then I declare, yes, and then I declare a pointer, oops, aiuto. Okay. Then this is horrible how it was indented. This was a unique line. Then I declare a pointer to a class BLB that I call B. Okay? This is a pointer. And I assign to this pointer the value of an expression. It's an assignment. It's an expression what you have on the right. What is the value of an expression? Is the result of the call of a function dynamic cast BLB star to a pointer. What is this operation doing? Takes the pointer to this object over here, and it tries to convert it with reason to a pointer of an object of class B. That clear? In doing so, what the system is really doing is going into the class object, into the instance of the object, reading one member that you can't see but the compiler can, which points to the virtual method table. The virtual method table is this table of pointer which is shared between all classes of the same type. And it's one single instance, right, for all of them. And it checks, hey, is the address of the virtual method table of this instance equal to the address of the virtual method table of this other instance? And if it is the same, then the two items are the same object. So in this case, what you expect to happen is that the dynamic cast will fail because BLB, because A pointer is truly a pointer of class A, and B is a derived class, so the cast cannot succeed. On the contrary, another important thing, once you have a pointer of a method of class A, you can only invoke the members of class A from that pointer. You cannot invoke the members or the method of the derived class. However, in order to invoke, to lift it, what you can do, you can try to lift it. If the dynamic cast fails, means, no, I can't do this operation, no? This object here is more specialized than the object that you're asking me to cast, then it returns 0, which is a null pointer in C. In this case, same expression, but we do the same operation on B pointer. And in this case, the operation will work, and B will be equal to B pointer. Okay? Dynamic cast is a little bit of an expensive operation because it requires to crawl through the virtual method tables. Not dramatic, but in a nested loop, you might feel it.
Is dynamic cast a function of C?
Dynamic cast is a function is a operator of C.
Oh, okay.
One of the many operators in RTTI is in the C runtime. Is there?
So I didn't get the virtual methods table is common to the hierarchy of the classes, or
Okay. Okay, now let's think about, let's think that we're doing the things in C, right? If we're doing, how many of you did operating systems? Okay. You know what I'm talking about for the others. Let's say, how does inheritance really works? Okay, in Java, in any language. It works in this way. Inheritance, especially for the overriding, is a mechanism through which you have the selection of the right method. Okay? Now, how do you, it's obvious that every function has also a start address in the memory, right? That's called a pointer to a function. Okay? Now, what happens when you define a method? What is the virtual method table? Virtual method table is nothing else than an array of pointers to functions. Okay? when you declare an object that contains a virtual method, this means that there might be a time when you use that object that you might, or an instance of that object, that you might have to select to look truly at the identity of this object and to select which of this method to pick. Correct? Okay. Now, roughly saying, what you could do is to create a data structure that, let's call it object description. Okay? So every object is associated to every class is associated internally to an instance of the class object description. Agreed? So every class, every class is a category, right? Internally is below. What is a category? A category is a member of the class categories. Okay? Or category description. Every category has a category description. But the category description that captures all possible descriptions of all classes is by itself a data structure. And if you just like put in a hidden fashion into the instance of an object that contains a virtual method, you put a pointer as a data member, a pointer to the instance of object description. If you have another object of the same class, it's perfectly reasonable that this pointer, this member, will point to the very same object description, because the description is shared between all objects of the same class. That clear? Okay. Did I answer you? And this object description, so to say, virtual method table or virtual method tables, will contain whatever. And so if you want to figure out whether two objects have the same type, rudely speaking, what happens is that you simply compare the two values of these pointers to object description.
But the derived class will point at
that is not just a thing. That's the object description is organized in a diagram. So if you have a derived class, what happens is that you have another block that points to the previous block. So you have a data structure that actually implements and follows the hierarchy diagrams of the class. So you might require to crawl. Okay? This is what happens in the generated code. Have I been clear? Okay. Now, let's see, like I said, that C++ implements multiple inheritance, and let's see an example of multiple inheritance. I mean, how do you use multiple inheritance? Well, there are cases, we won't see many, but there are cases where basically you have a library made by someone. Moment. This is my favorite. Yeah, it was much calmer than last time. You might have a library made by someone, for instance, that implements, that requires to operate on some objects which are printable. And for instance, these printable classes, they derive a method print that you might decide to override. Okay? Meanwhile, you might work on let's say, a simulator for a robot, right? And you would like to start deriving your own classes, your own business, and whatsoever. At a certain point, so you have your system on a side. Maybe everything will be a member of a certain class word object, and then word object will be specialized and specialized any further, and there will be automatic functions that do display all the black magic. But then at a certain point, you decide that your word objects have also to be printable in order to use this other fancy library that is on the other side. And so what do? You say, okay, you know what? This object here is also a member of this other class. This instance is also a member of the other class. You implement the print method in all of your things, and then you will have implemented an interface. This is an example. Let's say I have a struct drawable that implements a method draw. I have a struct printable that implements a method print. Observe that I implemented them. What is this equals to 0? This equal to 0 means that this is an abstract class. An abstract class is a class that has at least one method which has this equals to 0. If you put equal to 0, clearly you don't need to implement it. Okay? Abstract class means a class that only defines an interface but doesn't have really a behavior. And you cannot create instances of that class, but you can manipulate pointers to that class. You cannot create instances because there will be undefined behaviors. The behaviors will be defined only in the derived classes. And you can also derive it only a bit, not all. You have partial, also abstract objects which maybe implement a few methods and not others. They will still be abstract. Okay? Well, here we have a fantastic method drawable, a fantastic method printable, and then we have a fantastic point, and then we have a point which comes from another library again that contains two variables, x and y. And then we might decide to create a printable and drawable point. To do so, the point will be will derive from point, will derive from printable, will derive from drawable. This means that if I have an object of this class, I can easily assign it to a point and maybe do my manipulations. Or I can operate on this object as if it was a point in all functions that accept it. Okay? Clear? And answer. And then here I declare these methods virtual. Here I will have to override them in order to fill the interface. Otherwise, I wouldn't be able to implement this interface. Okay? Now, this is my definition of the class. And then let's say I want to use this class. I have a method that I call rotate that takes a point as a destination. Observe that I'm giving a reference, okay? So it manipulates a reference. So this is the destination object on which I'm writing in. I have another point which is a source, and then I have, and then here I do the rotation. No, this is a rotation matrix, you remember, from robotics 1. In order to rotate a point, you have to multiply it by a rotation matrix. So cosinus sinus minus sinus cosinus. Right? And then you have this business over here, you write it to the destination, you're done. Then we might also have another method that we call drawAll that takes a vector of drawable objects of size, and then it will have fun in calling the draw method of all the objects that I have in. Okay? And then what we could do is like to declare a printable and drawable point P that has coordinates 1, 2. Another printable and drawable point PR denoting P rotated. Then we can have fun and call the rotate function that writes on PR, reads from P and applies a pi half rotation. And then we can invoke the method drawAll. Here I'm cheating because I'm invoking the method drawAll from a unit dimensional array, which is consisting only to the pointer of P. One dimension. Okay? And this will draw. Okay? Then one final thing, but we will not encounter this in a well-behaved design. Sometimes with multiple inheritance, with simple inheritance like in Java, you're fine because basically your class diagram is a tree. Okay? There's no chance that an object is contained twice. But in C++, with multiple inheritance, you might have that you have a class A, from which a class B and a class C derive, and then for whatever reason in your hierarchy you have a class D at the end that derives both from B and both from C. What happens technically? B contains an instance of class A. C contains an instance of class A. So in D, I have two instances of class A. One that belongs to B and the other one that belongs to C. Which one is the correct one? None. No, I messed up. You can solve this. There's a mechanism which is called virtual inheritance, but we will solve this by never doing diamond problem, because otherwise I would have to teach you 12 credits of C++. Okay? Fine? But if you're interested, look, virtual inheritance diamond problem, and you will find it. And then let's come to the juicy part, which is what I would like. What time is it? Oh, I don't know if we manage, but I will try. We would like to construct, with the concepts that we have learned today, up to today, a funky simulator, done yesterday afternoon, that supports multiple robots and multiple devices. In particular, it specializes for a special robot, which is a differential drive. What is a differential drive? Is a robot that can be controlled in tangent velocity, which means this sort of velocity, and angular velocity. Okay? So it moves on arcs of circumference, which are controlled by the ratio between translational and rotational velocity. And then we also would like to mount on this robot a LiDAR, but we would like to do a proper object-oriented design that supports multiple robots, like that we can do whatever we want. That we can put an object onto another object, and so on and so forth. We would like our robot to move in a map, which is a grid world, where every grid is an image, where every cell of the grid corresponds to a square of x by x centimeters. It's called resolution. We would like the word will be loaded by an image, but we don't have to worry about it because this part will be given. And the message is like the word is a black and white grayscale image, and then pixel darker than 127. So between 0 and 127 represents an obstacle. Other pixels are white. It's like in a grayscale image, 255 is white and 0 is black. The world is populated by multiple objects. The objects can be put on top of the other. What happens if you have a stack of objects? Well, that when you move the object on the base, also the others will be moving. Okay. Other specification. It's a simulator, so the system has to evolve in time. At each step, the simulator updates the world. We would like that each object, what happens? The simulator says one tick, one epoch has passed. And then it tells to all the objects which are contained within a object, update yourself, right? By implementing the by using the overriding mechanism. In particular, we will have a robot inside, one robot class. We might have many instances, right? That is controlling linear and rotational velocities, but we will go quick on it. We would like it to handle collisions, which means if it bumps against an occupied cell, it has a diameter, right? So you don't want the robot to go, if it's 1 meter robot, you don't want it to go half a meter or you don't want to enter into the wall, okay? You want to handle collisions, and we also implement a funny LiDAR sensor, which is a laser scanner. An object that is able to, it's basically, have you ever seen a laser meter? Take a laser meter, take a mirror on top, start moving the mirror this way. What happens to the beam? It gets deflected, right? That's it. So you can measure the distances along a set of rays. That's a line. Okay? And then there are exercises. Now let's see. I would say 5 minutes break. Are you calm? 5 minutes break, because then I have to load up. And you have an implant before. I know you want to escape, but wait a second. First, the spoiler, right? Test data. Okay, this is what we have. Now, here I put two laser scanners. Here I put two laser scanners. I'm loading a map. Okay. You see the laser scanner measures the scans, so to say the distances, the ranges, and I'm controlling the robot. This little ugly black dot is the robot, right? And it simulates a laser scanner. What happens if I try to go backwards? Here I'm trying to go to the wall, but it hits the wall. So no, I don't go any further. Okay, I have to go backward a bit. Be a well-behaved robot. Okay, that's it. Now 10 minutes break for 25.